So do you know 32% of users on an average abandon your website if your website speed is greater than 3 seconds, and this is a study conducted by Google. And have you faced any frustrating situation when navigating a website or trying to purchase something, and have you felt any frustrating moment, or what is your frustrating moment when you go to a website? The spinners, loading spinners, right? I always get frustrated when I see that. Okay, so if your application or if your business is purely dependent on the digital presence, and if you are a commerce website, or if your business runs based on the digital presence, then website performance is more important. And how the website performance is measured is based on Web Vitals. So if there are any web developers in this room, so you might be knowing what Web Vitals is. It is the way how to measure your website performance. And it has three parameters. The Web Vitals score has three parameters: FCP, LCP, and speed index. The first contentful paint, the largest contentful paint, and speed index. And all this is dependent on the backend APIs, because your entire website is going to be painted based on the data from the backend APIs. So if your APIs is not performant, and if your APIs is not providing response on time, obviously your web page is going to have that spinner, and we want to come out of it. Why do we need to come out of it? If not, you are going to be penalized by the SEO engines. So your website will not be ranked top, and you will have a very bad consumer experience, which would also have brand impact and lack of trustworthiness within your consumers. Last but not the least, which is the critical piece, there will be a low conversion rate. As I said, if your business is purely dependent on digital presence, and if your website is slow, the conversion rates will go low. Okay. And as per Google recommendation, the response time from the backend API should be less than 500 milliseconds to paint the page. If not, it is going to have hit on the entire Web Vitals score. Ladies and gentlemen, good morning. Myself Meiyappan Kannappa, as Cliff said, and I am the Director of Technologies in the Ford e-commerce space. We are building the e-commerce website within the Ford Motor Company. And throughout the session today, I am going to take you with two use cases that I have faced in the past decade. One is on the connected vehicle space, where we have to build API in less than 2 seconds because it will have an impact on the dealership. And this application is used by the dealership, wherein in the web portal they have to derive the software updates for all the control units in the vehicle. And the number of control units may be between 40 to 80. And for each control unit, the API will be called, and if the API is not performant enough, it is going to have impact on the dollar value to the dealers. And second one is on the mobility use case, very similar to our Ubers and Ola, wherein I want to search a cab or I want to search some mobility services, and how did we improve the API response time to make our web pages and the mobile page loads faster. So these are the two use cases that I will take as reference throughout this session. So typically when we build a web application, so this is the model that we build, right? So it will have a layered architecture. So you will have microservices at the backend, and as said in the previous session, right? So a single microservice cannot provide all the data that the user is looking for. The microservice will have a lot of communication internally. There will be a microservice to microservice communication, or there will be communication with the legacy services. And then there will be a BFF layer, which is called as the backend for front-end layer, which would also expose an API, and that would be consumed by the web application that is running on a desktop or a mobile device. This is a traditional layered architecture that I have seen building the web applications and microservices. This is really good, and we use REST API as the standard across all these layers for other consumers or for other applications to consume. This is really good. And the good part about HTTP 1.1 is, right, it has a universal browser compatibility. It has a it's more familiar with the RESTful API paradigm, and we all know how to build REST APIs by using JSON request response structure. There are no issues, right? But still there are some constraints using HTTP 1.1. It has a head of line blocking, meaning if any packets of data are lost, it has to resend the data from the first sequence again. So this is going to have an impact on your web page if this kind of situation happens. Second, it has a constraint on the number of connections and resource overhead. And the third key problem is the serialization process. How many of you know the slowness of your API, can be because of many reasons, but the key reason is the serialization and deserialization process. If your JSON is very big, if your request or response payload is very big, and if you want to serialize and deserialize, in many cases, the serialization and deserialization process takes a lot of time than to query the data from the database. This we have evidently seen, okay? And that's a problem with HTTP 1.1 building REST APIs with JSON as the request response format. And it also, it doesn't have a bidirectional streaming. It is always a one-way communication. You need to have an HTTP client which will make an HTTP call to the backend server to get the data. It doesn't support the bidirectional streaming. So what comes to the rescue? So what are the other options that we have in the industry? There are a lot of other approaches and paradigms that are available that we can use to enhance the website performance. So what are those? And most of you might be aware, one option is using gRPCs. Okay, how we can enable service-to-service communication with gRPC? Okay, so gRPC again stands for Google Remote Procedure Calls, and it was open sourced by Google in the year 2016, and it works on top of HTTP 2. That is the first advantage. Whatever drawbacks that we have seen in HTTP 1.1, that can be overcome using HTTP 2.0, and interestingly, gRPC doesn't work with JSON, it works with protobufs, which is more efficient than JSON. And the problem that I said, right, the serialization and deserialization, that would be 75% efficient if we are using protobufs. And again, this gRPC style can be applied to your microservice to microservice communication, the inter-service communication. It cannot be directly applied for the websites to interact to the backend service using gRPC, but rather if at all if you have a lot of microservice which has to communicate with each other, then gRPC could be one potential option, wherein with a single connection, you can have multiple request and response. Unlike HTTP 1.1, wherein for each request and response, you need to have a separate connection. But with gRPC, you can multiplex multiple request response over a single connection. So with this, the number of threads that is required for your application or to serve multiple request response can be highly minimized, and this would also have a direct impact on your cost on the resources. Okay. And whatever benefits that you got out of HTTP 1.1, right, be it in the kind of authentication or type safety, so all that is available even with gRPC as well. And gRPC have 4 communication patterns. So unary pattern, client-side streaming, server-side streaming, and bidirectional streaming. And this was lacking in the HTTP 1.1 or with REST API. And definitely there are use cases for this as well, right? So when we have service-to-service communication, the two services would need bidirectional streaming, or one service can send stream of data to other service. We have seen such kind of approaches that was required for the use cases that I mentioned, especially for the connected vehicle use case. Okay, and this is how typically a gRPC system works, right? So you will have a gRPC runtime both on the client and server, and then there will be a serialization and deserialization process that will be happening, which is called as the encoding and decoding, and then the client application or server application can get the real data what it is intended to get. And with this, right, we were able to get these improvements. So when we applied this gRPC to our connected vehicle system, wherein it has to interoperate with multiple other systems internally in other portfolios, we were able to achieve 75% of efficiency when compared to REST APIs and JSON payload structures. And it also, as I said, supports multiplexing. I don't need to establish new connection, and because once the connection limits exceed in one particular application instance, I need to spin up additional instance to scale it vertically, right? So we were able to achieve efficiency even in that aspect, and the headers would be compressed when we are using gRPC. So that is the other advantage when we use gRPC. So overall, how the response time looked like when we leveraged gRPC, I will show you at the end of the comparison with just with REST, with gRPC, and what are the other options available and how did we lower the response times. It is at the end of the slide. On the right hand side, you can see the comparison between REST and gRPC. Most of the parameters, gRPC outperforms HTTP 1.1 or with the REST API. So now we have enabled gRPC for service to service communication, which is really good. But in the first slide, I show you a layered architecture, right, where we had services, we had a BFF, and we had a mobile and web app, which is rendering the pages, right. So if it is a desktop application and if a page is rendered in a desktop application, you would be showing a lot of data. For example, if you go to a accounts section, right, so you can see your user profile, your address details, orders, everything would be shown in a single viewport. But if it is a mobile device, right, I will not be able to see everything in a single viewport. So it can be in 3 pages within the mobile device, right. I will see a user profile and then I can click my addresses and it will open me the addresses section, and then I click my orders to see my order section. But what happens is I will create a single endpoint which dumps all the data to the device or to the viewport, and then I have to parse and render only the sections which is needed. It is highly inefficient, right. So how can we enable the client devices to query for the data what it needs to show in the device? So that's where the next approach comes in, which is GraphQL. So you can enable GraphQL so that the client can query the data that it requires rather than the server pushing all the data to the client. And this is more efficient because again the process of serialization and deserialization benefits here as well, because for the mobile app I just need 4 attributes or 5 attributes to display in my page. The mobile app can query only those 4 or 5 data points from the server rather than getting the entire JSON, right. So this is a key benefit of using GraphQL. So in our use case, what we did is we enabled a BFF layer with GraphQL. So instead of having multiple REST endpoints exposed in the BFF layer, we enabled couple of endpoints enabled with GraphQL, and we had a very detailed schema, and the implementers or the integrators of this GraphQL, be it the web developers or the mobile app developers, they can write their client by querying the data that is needed to render their web page, rather than making multiple API calls to render the page, or rather than making one API call, getting a dump and then rendering the page. It can be more efficient with a single endpoint, and client queries whatever data that they need. So we enable GraphQL in the BFF layer. Again, as I said, BFF is a backend for front-end layer, which is responsible to do all the transformation, manipulation and aggregation of data that is required for the consumer touch points, be it your mobile or mobile device or web device. So with GraphQL, again, these are the improvements that we were able to achieve. The number of REST endpoints that we were about to call from the mobile device considerably reduced. It was around 3 to 4x reduction in the number of API calls that we need to make, because every network call would add performance delays in the page rendering time, which would also have impact to the web vital score, which I mentioned earlier, right. So that is a key benefit, and it also improves the developer experience, the front-end developer experience. The front-end developer doesn't have to write a lot of API integrations to query variety of data. Rather, they can integrate with a single endpoint, and based on the page, they can query the data like we query the database. They can query the GraphQL to get whatever data that they are looking for. So there is a developer experience improvement as well, and overall there is a data efficiency as well. So if I am getting 100 attributes in a JSON structure, and if my mobile app requires only 6 or 7 of it, I get 93% efficiency on the data transfer between the BFF layer and the consumer touch point. So these are some of the benefits that we got out of GraphQL. And overall, this also attributed to our reduction in the API response times, as well as improved website performance. And then moving on, right. So we have gRPC now for service-to-service communication, and then we have enabled GraphQL at the BFF layer, which is really good. But then every time when a consumer requests for a data which is not a transactional data, the request have to travel from the device to the BFF all the way till the database to fetch that data. Isn't it unnecessary? If the data is not changing very frequently, why do we need to allow these many network calls across the ecosystem to get that data? And my friend in the previous session also talked about this caching strategy, right? And exactly, we can leverage caching strategy. There are different types of caching strategy, and there is a mechanism where we need to place this caching. You can enable caching on your client device, or you can enable caching on the edge or content delivery networks like Akamai or Cloud CDNs, or you can even have a caching layer with Redis in your microservices, or you can enable the caching at the database layer with Postgres. Now they offer an in-memory cache, right? So you can enable or place your cache in any of the layer. But for a typical web application which is going to serve the B2C consumers or for the digital applications, right, what would be the right place to have this caching strategy? So that is a key point here, right? So caching is always a gift, but it also a curse. The reason is, many a times I have seen this as the architecture. So the cache will be placed in every layers. So if I have 5 microservices, every microservice application team would have a caching layer with Redis. They have a database, they would also have a caching layer, which is good. They can maintain their SLA. If they say their API has to respond within 500 millisecond, they can serve it from Redis and they can maintain their SLA. But if you take holistically from the organization perspective, right, to serve a web application, I have 5 layers of cache. My cost is going to go up. And trust me, with Redis, right, so normally a Redis at a production grade cost you around $500. And if there are 5 microservices, you are going to spend $2,500 for Redis alone, which is more than your database. So this is what I have seen many a times. But what is the right way to have this caching strategy, right? On this use cases where we need to serve the web content to the mobile and web device, and where it is a B2C application, the ideal place would be to have your cache at the CDN layer. So because it is not just the data, so if it is a server-side rendered application, or if you have a web server which is going to serve all the content, so you can cache the entire content that is required for your web page to render in the CDN layer, the content delivery network. The content delivery network are designed for that. So for this use case, we can leverage the content delivery network where the entire data would get cached, and that will be the ideal place. So still you can achieve the web performance and you can serve your web page in less than 500 milliseconds, and it would also have a cost efficiency. Okay. With these 3 strategies, right, by implementing gRPC for service to service communication, and by enabling GraphQL at the BFF layer, and by having a caching strategy at the content delivery network, we were able to reduce our overall response times. So if you see on the connected vehicle use case, when we started, the API response time to reach the web layer was around 2100 milliseconds, just with pure HTTP 1.1 with REST API paradigm. But when we implemented gRPC, GraphQL and had a caching strategy, the overall response time got reduced to 630 milliseconds. And by the way, this is 75th percentile, not 95th percentile. We have still opportunities. So we were able to reduce to 630 milliseconds. And on the mobility space again, so previously we used to get the responses to render or paint our page in 1500 milliseconds. But with all this, right, so we were able to reduce it to 230 milliseconds. And by implementing each of the approaches, we were able to see a considerable improvement in the overall response times. Does it stop here? Are these the 3 strategies? Are there anything else? Definitely there are multiple other options that we need to fine tune to enable the API performance and in turn to improve your web page performance, right? So even before we do this, right, so we need to look into these factors. Because implementing a gRPC or a GraphQL or a caching strategy as a maintenance and the cost overhead, right? So does your application really need it? For example, it may be a bad example. So if you are using a payroll portal to view your pay slips, right? Does it require a high performance website? You can compromise, you can trade off, right? We don't need a highly scalable or a highly performant architecture over there. It can still live with the traditional REST APIs. So these approaches are required only where your business is highly reliant on the performance. And even before we get into there, right, we need to look into some of these factors which would influence your API performance or your web performance, right? So first is on the server infrastructure. So how are you slicing your servers, be it VM or the containers running in Kubernetes or even a Cloud Run instances, right? So you need to rightly size that, be it the CPU or the memory or the bandwidth, right? It has to be rightly sized. So if you are having 500 milli CPU and if you want that application to serve 100 requests per second, that is not going to happen. It is going to give a poor response, right? And second thing is on asynchronous API. So wherever possible, for microservice to microservice communication, you can rely on asynchronous APIs or event-driven architecture, so that you don't have to have a real-time integration which would in turn improve the overall web page performance, because it is not dependent on other service in real time. Rather, it can like fire and forget, or it can work based on the events. And it also dependent on your database performance and query, right? So you need to rightly size your database, and your database queries should be properly indexed. If not, that is going to delay the time, whether it is gRPC or REST, right? If your database is not tuned properly, you are not going to get the response in the right time. And yeah, the request and response payload sizes. I have seen some of my teams, right? So just to give certain data, they would be dumping the entire JSON from the database access. So the API have to be designed properly. So you need to work with the consumers of your API if possible, and you need to understand their use case, and you need to have the right attributes. And sometimes I have also seen, right, for enabling backward compatibility, they will add optional attributes to the JSON, which will in turn increase the overall response payload size, which is not the right approach. So you need to consider these aspects as well. And the cold start times, right? So if you are doing vertical scaling during peak time, if it is a Spring Boot application, on an average it takes minimum of 10 seconds, right? Is there any alternatives? Can we use GraalVM? Can we use Spring native images so that the cold start time can be reduced? So you need to look into those opportunities as well. And the network calls. As I said, if your website, once it loads, if it makes multiple request calls to paint the page, that is not going to look good. So how can you optimize the number of network calls so that your consumer experience is not impacted? So these are some of the influencing factors you need to look into before we even get into a gRPC or a GraphQL approach introduced into our architecture. And last but not the least, right, if your application is in Kubernetes, right, so you need to have the service-to-service communication within the Kubernetes network or with Istio. Again, this is some of the mistake that the teams would do, right? So they would make a call to the API manager, and the API manager will again route it to the microservice. So from the two applications will be running in the same Kubernetes namespace, but it will go out of the network and again it will come in. So you need to see whether there is any opportunity so that there can be a service-to-service communication within the Kubernetes network. So these are some of the influencing factors for the API latency. And we have come to the end of the session. What are the key takeaways in this session? So we started with the traditional REST APIs, which is really good, and it is still good. But what are the other alternate approach so that we can still improve the performance of the web page rendering times by using gRPCs and GraphQLs, maybe gRPC for service-to-service communication and GraphQL to the web to the BFF layer communication, and what are the caching strategies and where we can position the cache in an optimal way, in a cost-efficient way, and what are the trade-offs and value propositions that we get when we enter into gRPC and GraphQL world. As I said again, you need to have that mindset to do the trade-off, whether it is cost versus ROI or it could be the operational overhead. So you need to have some operational overhead and you need to have some trade-offs before you decide on the right architecture. With that, it's the end of the session. Thank you, everyone. Questions?
Yeah, we have a couple of minutes for maybe one or two questions.
Sure.
Just opening it up. Anybody would like to ask some questions?
I think that was a very useful session.
Thank you.
For me. Just one question on the caching architecture you showed, right? Where you had the caching at the CDN level. Now I understand that for something like users address very static data, but order data, how does it make sense to have it at a edge level caching? Because there will be multiple updates happening on it, right? During that time.
So you need to have the right caching strategy defined, right? It is not just caching. So when would you invalidate the cache? When would you evict the cache? So all that would come into picture. Most of the time, right, when I place an order and if the order is into the database, the probability of that order getting changed into a cancel state or edit state would be very minimal. And even if that happens, right, the approach that we took is event-driven cache eviction policy. So whenever there is an order update that happens, right, so we will evict the cache and rebuild the cache, or we will leave it as is so that the data will not be in cache and it will travel all the way to get the orders cache. So you have approaches to handle this.
Sure.
Cool. Maybe just one more question.
Yeah, this is Arul from Honeywell. So I just want to know, we have a traditional REST services. So I understood the gRPC calls service, that's fine. But what about this GraphQL to the traditional approach? How do we integrate that GraphQL and reduce that time? So I just want to know the
Okay, so
integration part.
GraphQL still works on HTTP 1.1. Okay, so instead of having a REST API, GraphQL is another paradigm very similar to REST API. It still works on 1.1. But the difference or the differentiating factor is with GraphQL, you will have a predefined schema and the clients can request the data what it needs. For example, you can have user profile data, address data and orders data. But on the mobile device, when I click orders, I need only the orders information. So from the mobile device, I can make a request to this GraphQL endpoint asking only give me the order ID, order details and order pricing. So though it has 10 or 12 parameters, the response will contain only the order ID, order code and the order price in it. So the response or the data size that comes from the server to the web application would be very minimal when compared to the REST endpoint which has all this data as a JSON. So this is one aspect. And second, what was your second question? Sorry.
So how do we, like, suppose I have a existing APIs, right? So do we need to migrate to this, or how it is? How
you
it
need
works?
to, you need to migrate to it. It doesn't natively support, so there are libraries and frameworks available. So there is something called as Apollo GraphQL, which can be used in the Node.js layer to build the GraphQL endpoints. Even with Spring Boot, there are Spring GraphQL libraries you need to use, and then you need to expose the GraphQL endpoint.
So just last one.
Sure.
So for example, see, I have a API which is going and connecting a database, which takes a lot of, for example, the load of database, the event size is more. Like for example, existing, it was taking too much of time. So with this GraphQL, can we moderate and can we get it sorted that?
It can be, but again it depends on how you design this GraphQL endpoint and how this GraphQL endpoint will interact with the database or with other microservices. And as I said, this GraphQL will be used in the BFF layer. Typically in the BFF layer, we would not make any database calls. So if I look for an order information in the GraphQL layer, it needs to connect to the order service, order microservice, and that would in turn connect to the database. So typically in the BFF with the GraphQL, we will not make a database call. So you need to design it in a way so that it doesn't have an impact.
Thank you.
Thank you, Meiyappan.